Welcome to the Explainer team. I'm really glad you're all here. Look, today we are literally tearing down 80 years of computing assumptions. We're not here to just iterate on some legacy code base. We are here to fundamentally rewrite the rules of how silicon interacts with state. You know, as engineers, we've basically been taught to respect the boundaries of hardware, right? But today, we're going to look at the Phoenix construct. It's an architecture designed to completely shatter those preconceived notions of computational limits. Okay, let's dive into this.
So why are we still fighting physical bottlenecks? Seriously, every single day, as developers, we hit the exact same wall. CPU cycle limits, memory bandwidth starvation, not to mention the sheer heat and energy cost of spinning up 1,000 virtual machines. We tend to treat these physical constraints as like unchangeable laws of nature. But what if our reliance on physical silicon constraints isn't actually a hardware problem at all? What if it's just a solvable math problem that we've been approaching from entirely the wrong angle?
To fix the future, we really have to aggressively attack the past. Section 1. The von Neumann fallacy. The end of computing.
In the legacy von Neumann world, the world of temporal linearity, the CPU is basically this actor just trudging through a static landscape. It fetches an instruction, performs an operation, stores a result, ticks a clock, and repeat. It's inherently destructive, it's slow, and it's strictly linear. The Phoenix construct, however, recognizes that the universe doesn't actually calculate its next state, right? It simply exists as interacting fields. So we're doing something wild. We are deprecating the clock cycle entirely. We're moving into the consensus world, which is driven by the manifold phase.
Section 2. The holographic manifold. Topological boundaries. Now, what's really interesting about this slide is how we're replacing physical partitions with topological boundaries to rebuild our foundational substrate.
Following the holographic principle from quantum physics, we treat the physical storage medium as a 2D boundary that encodes a higher dimensional mathematical space. Now listen to me closely here, team. The CPU is no longer a calculator. It is a physics caliper. And your hard drive? It's no longer a filing cabinet. It is literally an equation container. We're making a massive shift from simple data movement to actual resonance induction.
Now I know exactly what you're thinking. Oh, this is just theory. But look at the C++ hypervisor code running bare metal, mapping the physical anchor. We aren't just theorizing about quantum states. We are actively compiling them into a zettabyte-scale virtual address space using just a 4.01 gigabyte physical mirror file. Basically, we're mathematically projecting a massive topological field into a fixed physical footprint. The hardware is simply the anchor.
So how on earth do we run thousands of systems simultaneously on this architecture? That brings us to Section 3, Resonant Frequency Partitioning, Infinite Branching.
In legacy virtualization, you know the drill. You build rigid memory walls between virtual machines. Well, we don't do that. We use isolation by resonance. VM instances act as wormholes, defined by derived resonant frequency seeds. Through a really elegant concept called harmonic inheritance, the hypervisor stores only the differential residue. Think of it kind of like a git commit, right? It's an XOR bit mask differential between a master's baseline reality and a guest's mutation. They share the exact same ground truth, but they only consume new memory when they actually diverge.
I really want this core philosophy to sink in. Just as different radio stations occupy the same physical space but do not interfere because they operate at different frequencies, infinite Phoenix timelines occupy the same substrate manifold. We aren't just slicing up a pie here. We're broadcasting on different frequencies. This means infinite host realities can occupy the exact same physical hardware footprint without a single drop of cross-tenant data leakage. It's a total game changer.
And because of that brilliant isolation, the mathematical complexity of spawning a new timeline absolutely plummets to this jaw-dropping metric, big O of 1. Legacy developers are super used to linear, O of n scaling. If you want 10,000 parallel VMs, you need 10,000 times the RAM. Not here. No way. It costs 0 bytes and 0 nanoseconds to spawn a new timeline because we aren't duplicating data at all. We are merely tuning a new coordinate transform in the manifold.
And this brilliantly illustrates our sub-Shannon reconstruction logic executing 20-bit residues, perfectly demonstrating the absolute magic under the hood. In this trash compactor phase folding process, we predict the output, calculate the divergence, and store only the tiny 20-bit differential residue. We're reconstructing the data on the fly, based purely on mathematical resonance.
Which naturally leads to this staggering physical reality, a 1,000 to 1 density collapse.
To put that into perspective, we take a 10 terabyte kinetic reality, which is normally enough to fill an entire server rack, and we compress the whole shebang down into a 3 gigabyte physical residue journal. We are effectively using time and topological interdependency as our actual storage medium.
Section 4. Spatial Transduction Execution. Bypass the FTE cycle. Storage is only half the battle, right? We need to shift to processing, completely leaving behind the miserably slow fetch, decode, execute legacy cycle. In the Phoenix architecture, legacy x86 or ARM opcodes are no longer treated as commands. Instead, they are geometric intents. The answer to our logic already exists in the mathematical space. We don't actually have to calculate it sequentially. The physical silicon simply observes where the topological intent collapses into a result. The hardware is literally just watching the math resolve itself.
Here is the exact execution sequence. Step 1. Backwards transduction. We actively measure the topological slope of the manifold. Step 2. Singularity collapse. Instead of brute-forcing computations, our roaming calipers, which are the CPU cores, synchronize their phases to find the intersection of the intent. And finally, Step 3. Materialization. The result is pulled directly from the coordinate space. We're talking about logic resolved at the speed of the memory bus.
Let's move to and see how this builds into our ultimate payload. Section 5. Mathematical quantum supremacy. A mathematical problem.
This right here is our defining thesis statement. Quantum supremacy is a math problem, not an energy or cooling one. By treating data as its own physical universe and the computer as a balanced system designed to observe that universe's movement, we have successfully unlocked quantum state complexity on classical 20-year-old hardware. We absolutely do not need supercooled, entangled qubits to do this. We just needed better math.
Make no mistake, team, Phoenix is not a simulator. We are definitely not faking this in software. The hypervisor is a computational interferometer. It measures the resonance of information itself. We are no longer bound by the massive energy cost of calculating reality. We are only bound by the precision of our calipers measuring it.
I'll leave you with this final thought as you prepare to dive into this codebase. You've spent your entire careers hitting the limits of the von Neumann bottleneck. Well, the door is now open. The manifold is live. Are you ready to stop calculating reality and start measuring it? Let's get to work.